So, good morning, gentlemen. So today we'll be going to discuss about a small problem in terms of 4 different cases with the aid of ANSYS workbench. So first of all, I've taken a problem from an website that is a cantilever beam. As you know well about a cantilever beam, a load which is acting on a free end and constrained at another end. So we can think it of many different applications such as swimming pool jump pad or else any hanger which is fixed on one side of the wall. Likewise, different application you can consider for a cantilever case. Sometimes for defense application or aerospace application, you can consider your wing aircraft wing. One end is fixed on the fuselage and the other end is free where the aerodynamic load is acting. So back to the case. So from this cantilever beam, you will be finding deflection, stress, and stiffness. That is the first case. And second is how do you find SFD and BMD with FOS? Shear force diagram, bending moment diagram, and factor of safety. Similarly, how do we optimize the structure based on the application where the load is required and where the load is not required? And at last, we'll do the validation with an aid of analytical calculations or calculate the value with the help of formulas that will compare with the software results. Fine. All right. So now you back to your workbench and open a static structural, double click the static structural, replicate in on here, and you can double click over here to right cantilever beam, use underscore beam, a 3D case. Similarly, you can solve the same cantilever problem with 2D and 1D also. Most probably 1D will give a best results than others, but for 3D will give a real feel. So since the problem has a uniform cross section, we can play with the 1D, but since I want to do some validation and other stuff, so 3D would be better. Sometimes you can cross check your results 1D versus 3D of the same cantilever beam and see how well it look like. So you just double click your geometry so that in the left bottom you will see starting design modeler will open with analysis type 3D. So once it is open, you just draw this one with appropriate dimensions. So that is in terms of meter, keep it in terms of meter. Just roll in to see that axis first of all. So XY plane, then center fit. Go to the sketching, pick the rectangle, and draw it in the middle. So use constraints, select symmetry, select this axis with 2 lines, right click, new symmetric axis, select this, Now I go back to dimensions. And V1. Yeah, V V V V2 is nothing but your 0.06 and H1 is 0.1 meter. So this is what a cross section you have, and the length is about 0.5 meter. So click modeling, click extrude, and select horizontally, expand XY plane, select the sketch, apply, put 0.5 meter, and generate a big into view with the isometric view projection. So you can minimize this and go to the model for doing machines. Engineering data, geometry, and model for the pre-processing, where setup is a solver setup case and solution is your output, and result along with the solution actually. So it is opening a new window like a mechanical. Let it load. Well, once the model is on this interface, but just check it out the material property whether it's by default material patched or not. That is structural steel. Structural steel properties will be patched. So right click, generate the mesh by default, because meshing is a very broad concept. So I don't want to talk about much right now. So just expand the statistics. So 240 elements with 1471 nodes are available. So now back to the static structural and click the environment. So pick fixed end on the one face, and the load is or the force is applied on the other side. So you can use rotate button and click on this face, or you can select with the help of this filter to apply the load on the edges too, if you're required. Okay, I'll select the load on this edge, apply, don't forget to click apply. So component wise, along the y direction, 1000 newtons, so negative 1000 newton. All right. So one it is fixed, and this load is applied. So what is the output we want first of all? So total deformation and stress. That is one measure stress, which is uh, very important and frequently using to check out the failures. So once you select the required outputs, you will see the results. So once it's solved, it got a tick mark on the left side. Now see, this is what the deformation which you got is 0.11603 mm, and the stress is actually 8.13 megapascal. Okay, is acting on here, more on here. This is for 240 elements. Okay, so you can take these two results as a reference. So what is the deflection value? I'll write it in here. So deflection for 240 elements of 1470 nodes, whatever. So 0.11, I forgot the value first of all. So 0.11, 603 mm, and stress. That is, 1 measure stress will be considered for failure criterion. 1 measure stress is actually 8 point something, I don't remember. So 8.1374. 8.1374, right? 8.1374 megapascal. And stiffness, generally you speak, so load by deflection. So F by del, that is Newton per meter. So load is like 1000 Newton and deflection is 0.1163. So you take a calculator. So 1000 Newton divided by 0.11603. The value is about 8618. That is Newton. 8618.46. 8618.46 Newton per meter, or else approximately 8.6 kilonewton per meter, or kilometer per mm. So here's to mm. Because for deflection is 0.11, right? So that's it. So this is for the first case. We'll check whether this value is right or not. At last, we'll validate it. Now, second is we need to figure it out the SFD and BMD with FOS. So even FOS you can calculate with the help of the same 3D itself. So how? So click here, go to the toolbox and click the stress tool. So when you expand the stress tool, so safety factor will be replicated. Just find, evaluate the results. So safety factor is mentioning 15 as a minimum and maximum. So which means that factor of safety will play. So that I will tell you on here. Because once the load is more or huge, so the safety factor will be proportionally showing the results. Okay, now you just understood right the first case. Now for the second case, so double click the same, but cantilever beam. All right, let's go for 1D. Okay. So open the geometry, but this time you'll be playing with the 1D case, because 1D case only having the tendency to show SFD and BMD. For 3D case, you can't able to see SFD and BMD. So what you need to do is click the XY plane, click here, and sketching, go to the line, this is in meters, so set the unit system as in mm. So hit the line, select from the origin, and ends with here. So now set the dimensions. So h1, that is 0. Okay, since it is a meter, it's a 500 mm. Sorry, I guess 50 mm. So you just set the unit system as a meter, that's better. 0.5 meter. Good. Now you back to the modeling and go to the concept. This is for creating a line body. The line from a sketch what you have drawn. So click the sketch, apply, and generate. So now you got a arrow mark indication towards from left to the right, and this is what your line body. But this line body doesn't have any cross section. You need to create a cross section by the help of tools. go to the go to the concept with the help of concepts. See the cross section. Select a rectangular. So rectangular along the breadth is 0.1, and at the height is actually 0.1, but breadth is 0.06. So now look at the line body. So double click the cross section and click view cross section solid. So you will come to know how the bodies look like. Fine. Once again. Yeah. So what we need to do the next is very simple. So we just minimize this and double click the model so that it will open a new mechanical, but not a old mechanical in a 3D. So after creating your first case, second case, that's a 1D. So here's the material, line body. Here's the material by default structural steel I applied. So cross section rectangular cross section, and the meshing is, I'm just going ahead with the default meshing. Look at here. So since it is a uniform cross section, so for a uniform cross section, it won't disperse along the y direction. It will disperse only along the x direction itself. That is what the speciality. I can go with more number of elements too. So in terms of now, right? So 1 mm. You just disperse with the help of 1 mm and generate the mesh. So now see how it's, but it is not vertically dispersed. It is dispersed only the x direction. Okay. So now the same fashion. So go to the static structural, pick the point first of all, and go to the environment. So fixed on one end, and the same the load is applied on the other end along the y direction. So double click the defined by and select the y direction as negative 1000 Newton. All right, now solve it. So you'll be getting the results as quickly now. And also in solution, it won't be shown any stress, strain, and all now. See, if you click this, so total deformation is the thing which is available, but for strain, nothing, stress, nothing, energy, nothing. Because these options will be suitable for only 3D case, not for 2D case or 1D case. Sorry, this is suitable for only 2D and 3D case, not for 1D case. For viewing the results on 1D case, we can go and see the beam results in a what is it for 1D case. So you can check out the shear force and bending moment diagrams. But for shear force and bending moment diagram, I don't have any outputs. I don't have any path first of all. So I need to create a path. For creating a path, I can right click the model, click insert, and construction geometry. That's a path available. So click the path. Another path and change the path type and click the edge first of all. That is the one edge we have, which we created. That is the only one edge. So for edge, click the edge first of all with the help of edge filter and click the edge. Then apply. Then back to here, or else you can rename this path with the help of F2. That is F2 here. line edge 0.5 meter. Okay, now you can pick the path what we just create a line edge 0.5 meter and right click, evaluate the results. So still the Air Force is not there. So in order to see your stress results, so click the tools, sorry, click the toolbox, select the beam tool, right click, evaluate the results. Now see, this is what the deformation. What is the deformation? 0.11703, 0.11703. So you just note down the values. For 1D, just selecting green color. Deflection, which is equal to 0.11703. All right, 73 or 703. I'm not good. Let me check it out. So 0.703. Yes. 0.11703 in terms of mm, right? Yes. Mm. Now stress. So stress. So stress, you can check it from the beam tool. That is the stress. The minimum stress is negative and the maximum stress is 0.8 or 8.333 or 8.3333 megapascal. 8.3333 megapascal. Now stiffness will be stiffness K, which is equal to low by deflection. So you can take a calculator. So 1000 divided by 0.11703. So 8544. 8544.817. 817 meter per mm or 8.5 kilonewton per mm. So this is what for 1D and this is for 3D, but still SFD and BMD is not yet calculated. So go to here and the SFD and BMD. You just click on here, automatically it will show here. So my SFD is maximum. First, there are three categories here. One is total shear force, that is the first. Second is bending moment, and third is total displacement, how much it is displaced and all. One second. Yeah. So my shear force is maximum at 0 and throughout it is constant. And my bending moment, which is maximum at 0 mm and minimum at half meter, I mean 0.5 meter. Similarly, the displacement is fixed on one end where displacement 0 at one end of the beam and the other end is actually 0.11703. Okay. Individually, if you want to speak, you can right click insert, select beam to resource, bending moment, and right click, evaluate the results. So this for the bending moment for individually 5 Newton mm, which is maximum here. Okay. If you don't require, you can delete it. And normal reaction forces also you can calculate. So just click on solution, insert. So here is a probe, and check it out, normal reaction of force reaction. So at the fixed support, it usually to be calculated. If it is a simply supported, then both ends will be considered. So right click, evaluate the results. So my reaction force is 2.3632 e power minus 14 along the z direction, and for y direction 1000, for x direction 0. Maybe if you want to calculate the reaction force on other side, which where the load is applied, so you can calculate accordingly. So location method is boundary condition. Sometimes you need points, remote points, or something like other cases. Geometry selection. Click this one. Select the dot. And select the dot here and apply. So, but force cannot be calculated with the vertices. Yes, similar with the outputs. Force will be calculated only on the fixed ends. So now force reaction is not required and delete it. So this is how we are seeing our SFD and BMD. But for FOS, so in the solution, right click, insert. You cannot able to see your other things like FOS, safety factor. The beam tools also, we could see only direct stress or maybe minimum combined stress or maximum combined stress, but we couldn't able to see FOS on here. But what is meant by the FOS? Your ultimate by the working, or ultimate load to the working load, ultimate stress to the working stress. So the ultimate stress is nothing but your material stress. Since this is a ductile material, so my ultimate my ultimate strength, or for yield strength, that's the compressive. But for case, so we can check it out from our workbench. So double click the engineering data. So look at the structural steel. So this is what your tensile yield strength. Yes, tensile yield strength or tensile ultimate strength. So 4.6 e power 8. So that is what the factor of, okay, let me write here. FOS, which is equal to, again, take in another color, blue, ultimate stress, 0 by the working stress. So ultimate stress is 2 point tensile yield strength you can take. Both are okay. But don't go with the ultimate. Go with tensile yield 2.5 e power 8 Pascal. Or in terms of megapascal, 2500, 2.5 100, that is 250 megapascal. Okay. So 250 megapascal divided by what is the working stress which we got actually here, the stress, that is I guess 8 point something, 8.33 megapascal. So 8.33. So you tell me how much this thing would be. The ratio is so bigger. So that is why that is showing 15. So 250 divided by 8.33, you can take a calculator. So 250 divided by 8.33. 3, 30 times. 30 times stronger than your system. So hence design is safe. Safe. There is nothing bigger design we designed. We taken a random model from Google and we done. But anyhow, the design is safe. Okay, now we need to do the optimization and parameterization. For optimization and parameterization, there are a lot you need to understand the scenario. There are multiple optimizations are there and multiple parameterizations are there. Shape, geometry, topology, meshing, boundary conditions, loading conditions, constraints, and lot. But talking about the numerical validation, we'll see now. So what is the general formula for, we'll take analytical calculation now, analytical calculations. So what is the stress formula? Stress, that is the bending stress we need. Since here bending has happened, bending stress may m y divided by I. That is what is the bending stress formula. And similarly for deflection, which is equal to P L Q divided by 3 E I. This is in bracket. PL cubed divided by 3 EI. Okay. And now we'll first calculate the bending stress, or we'll first calculate the moment of inertia, that is I. I, which is equal to, for rectangular cross section, BDQ by 12, BDQ 0 by 12. So B is your 0.1 meter. 0.1 meter multiply with within a bracket D 0.06 raised to the power of Q. Then whole thing divided by 12. So the value is around 0.123458 meter power 4. The unit is meter power 4. Meter power 4. And for bending stress now, bending stress, which is equal to, what is moment? The moment and this is moment of inertia. Moment of inertia I. Moment M, which is equal to force into perpendicular distance. So force is 1000 Newton multiplied with distance Y along the Y. So the cross section divided by 2. So it will be coming like 0.03. Y is nothing but 0.03, which is equal to, the moment will comes like, how much the moment, so that will calculate, and the bending stress. So 1000 into 1000 multiplied by 0.03. Sorry. This is perpendicular to this 0.5 meter, right? I'm so sorry. 0.5. And y is nothing but 0.03, which is a half of your cross section along the depth. Okay. Then the whole thing divided by I. What is I? That is 0.123418. So then what is the Bench stress you will be getting is nothing but 8.3333 Newton per meter square. In terms of mm square, it will be coming like it will be mm square. And for deflection, PL cube. So P is 1000 Newton into L cube. That is the length is around 0.5 raised to the power of 3, the length. PL cube divided by 3I. So divided by 3, and put a bracket 3E. What is E? 2E power 5. 2E power 5 multiply with an I. Or you can write 2E power 11 in terms of Pascal. Okay. Then 3I. I is 0.123458. So all put together your deflection, which is equal to 0.11574 mm. Okay. Now percentage of error analysis. Percentage of error analysis. So percentage of error from numerical to the analytical. So this blue color is nothing but your analytical calculation, where the red color is for 3D software analysis, and the green color is for 1D software analysis. So let us first figure it out the differences. So percentage of error, which is equal to input modulus numerical output minus analytical output, and whole thing divided by numerical output. Okay. Whole thing divided by numerical output. Numerical output. The entire thing multiplied with 100. Now to cancel the percentage. So what is the numerical value? You can take any one value, either it may be deflection or maybe stress or maybe stiffness. First, you consider the things between your analytical and software results, that is numerical results for deflection. So numerical output of a deflection is 0.11603 minus what is the analytical value of the same deflection? 0.11574. Okay, and the whole thing is divided by what is the numerical? 0.11574. Which one you need to take a benchmark? That you can take as an output here, like analytical minus numerical divided by analytical into 100. Okay, 100. You just take a calculator and find it out, the difference. So 0.11603 minus 0.11574. So 0.00029 and whole thing divided by 0.11574. So 0.0025 into 100. The value is 0.25% error. So 0.25 percentage of error between numerical and analytical deflections. Similarly, you can cross-check with the 3D results with 1D, or 3D results with analytical, or 1D results with analytical. Which one you feel comfortable, you can play with that accordingly. So this 0.24% of error is lying where? So the sources of error. So what is that sources of error? Sources of 0.25% of error. Where actually? Reasons. It may be anything. Maybe discretization error, or maybe linearization. Linearization error, or solver approximation error, or no, solver approximation in the sense ITT solver, or direct solver, or Newton-Raphson method, or some other methods. So that picking, sometimes algorithm, some, or material properties variation, maybe other things. Depends on the situation, what we consider. Once you rectify these issues, so you'll be getting the error as to be 0. We change the elements sometimes from 240 to more, or 500 or 1000 or 1000, 1 lakh, like, so you'll be getting a better result. So now I've just uh, talked about the case 1, case 2, and case 4. Case 3 we'll discuss in the next video. I hope so you enjoyed this session. If you have any queries, please contact in the below email or contact number. Thanks for watching.